In the previous section, we have been seeing on the T cell basics. I didn't only teach the T cell basics, I also told a lot of applications of how these T cells work. In the current segment, we are going to look on the B cell basics. Why understanding of this B cell basics is really important is because reason number one, 85% of the B cell, 85% of the lymphoid neoplasms are B cell neoplasms. I told this point already, which means you have to understand the in and out of the B cell. Second thing, understanding of this, how our immune system works is really, something very beautiful because they are so elegantly poised. At the same time, they are going to be a product of this much million and billion years of evolution. Our human immune system is one of the most advanced, and how super and elegantly it works is something really beautiful to understand as well. So that is why it's important to understand the B cell basics. I'm going to also discuss some of the applied aspects of the B cell basics as well. Before going into those things, let us understand the B cell development and the maturation process. Then in the second segment in the same video, we are going to discuss on the B cell activation process. Then we can lastly discuss on the somatic hypermutation, isotype switching, and the formation of memory B cells, and some important features of the antibodies that of the different classes of antibodies that we have. But before going into that, let us kick it on with the B cell development and maturation process. So I have drawn the diagram already in this particular video just to save the time. So you can see for this, first understand the stages of all these things. The first one is the hematopoietic stem cell stage, which it's completely undifferentiated. It's just a stem cell which commits itself into the B cell lineage. The moment it commits into the B cell lineage, I told you what makes the stem cell commit into the B cell lineage or the T cell lineage is very important. It's the absence of Notch signaling. I told you it's the absence of Notch1 signaling. So that is very, very important. This absence of Notch1 signaling is the one that commits the B cell to commits the stem cell to the B cell lineage. The presence of Notch signaling commit the stem cell to the T cell lineage, which means if you have a Notch1 signaling, the stem cells that are committed to some lineage will detach from the bone marrow and enter the peripheral circulation. So they enter the thymus and become B cells. But in case if you don't have the Notch signaling, they will stay and remain in the bone marrow and they will commit themselves to the B cell lineage. So lymphoid precursor commitment into the B cell lineage is determined by the Notch signaling, absence of Notch signaling. So this is the hematopoietic stem cell committing into a B cell lineage, which first becomes something called a pro B cell. Remember, this pro B cell in some textbooks, they also give it as pre B cells. But let me stick on to the term called pro B cells in this particular video in our future explanations as well. At the same time, this pro B cell also has two stages called early pro B cell and late pro B cell, which has its own relevance from immunological perspective but doesn't have that much relevance on clinical perspective. That's why I'm not giving any early or late pro B cell. For simplicity purposes, I'm just putting the pro B cell stage. Then it becomes something called a pre B cell stage. Again, this has two stages, early and late pre B cell stage, but I'm not going to discuss because of the no clinical relevance in that scenario. Then you have something called an immature B cell. Then it becomes something called a mature B cell. After becoming a mature B cell, it becomes something called a follicular B cell. Remember, this follicular B cell is nothing but a B cell that enters the peripheral lymphoid organs or secondary lymphoid organs. You can see that is why I put division here also. You can see that. So why I put that is because you have to know that it enters the secondary lymphoid organs. Even spleen, lymph node are the major secondary lymphoid organs, you know that. So that's where you get this follicular B cell. So in the follicle, they might spend their time without getting activated and they might die once their lifespan is over, or they might get activated and they can become something called an activated B cell. Activated B cell. So, or simply this also referred to as immunoblast. Remember, there are so many principles that happen within this activated B cell, but just this is a very simplest orientation which I'm going to give. But so much is there in the activation process itself. You have, like pre-germinal center, germinal center cell, centroblast, centrocyte, post-germinal center. A lot of things are there, but I'm not going to discuss in this particular section only. Later on, we'll go in details about all those things. Then finally, you have a plasma cell. This plasma cell forms the basis of the, like the reason for why B cells are there, because these are the plasma cells are the ones that are going to secrete these immunoglobulins, which is a primary function of why you have this B cell lineage, the humoral immunity. Anyway, this is the plasma cell. I have not talked about the memory B cell. I'll draw this in some time, the memory B cell one. So these are the different B cell, developmental types you have. Then I've divided into two compartments. One, you can see that I have put a compartmentalization here, and like I put a line here, dotted line here. Why I put this? Because this hematopoietic stem cell, pre-B, pro-B, pre-B and immature B cell is going to be present within the bone marrow. So they are going to be present within the bone marrow, and typically these are also referred to as something called antigen independent stages. These are also referred to as antigen independent stages. And if you go to the peripheral compartment, so the moment, like this transition line I've drawn here, the dotted lines, once you cross that, all these stages are nothing but these are peripheral compartments. So these are peripheral compartmental stages. They come out of the bone marrow, they be either in the blood or they're going to be in the secondary lymphoid organs. So these stages are called as antigen dependent stages, because the maturation of the B cells beyond in this particular stages depends on the antigen exposure. They are not, getting exposed to antigen means they will die in the immature or mature B cell stage itself or follicular B cell stage. They will not go for subsequent maturation and plasma cell formation. So that's why I told you these are antigen dependent stages. So anyway, so once if you know this compartmentalization, now let us move on to the basic principles of what are these bone marrow related stages and what are the peripheral stages. You can see, and one more thing I didn't tell you here, like all this process, you can see this, initially I told you that hematopoietic stem cell becomes a pro-B cell is going to become a pre-B cell is going to become an immature B cell, and immature B cell, you might be thinking, but it might become a mature B cell directly once it comes out of the bone marrow. Actually, it's not, to be honest. These are little bit more deeper immunology parts. So what really they do is they become a mature B cell all right in the blood or somewhere else, but before becoming a mature B cell, they enter a stage called a transitional B cell stage. These are generally called as something called transitional B cell stage. So what do you mean by transitional B cell stage? Is a B cell that comes out of the bone marrow doesn't actually go into directly become the mature B cell. This immature B cell, which I have drawn here, actually is going to become something called a transitional B cell. This is what we refer to as something called a T1 B cell in the blood. In the blood, it's going to become something called a T1 B cell. And this T1 B cell in the blood is going to enter the very important organ. I can draw something called a spleen. So they are going to enter the spleen. And the form of T1 B cells, they are going to enter the spleen. The moment these T1 B cells enter the spleen, there they have to undergo something called a selection process. I didn't talk much about the selection process in the B cell video. So they have to undergo something called a selection process, where they become either T2 B cells or they become T3 B cells. Suppose if they survive the selection process, they become this T2 B cells. Suppose if they do not survive this selection process, they are going to enter this T3 B cell, which means they are going to die in the spleen itself. They are going to die by apoptosis in the spleen itself. So if they become successful, which means the selection is successful in the spleen and they enter this T2 B cell stage, that is transitional B cell stage, what really happens is they form two situations. One, these T2 B cells may reside in the spleen itself. They might decide to stay within the spleen itself. And these kind of B cells, T2 B cells that have survived the selection in the spleen and decided to stay within the spleen, we are going to call it as marginal zone B cells. Marginal zone B cells. These are some specialized B cells which I have discussed in the spleen, in the initial basics of the adaptive immunity video, where I have told you in the spleen there is something called marginal zone, where you have a specialized B cell called marginal zone B cell. Certain B cells which decide to stay in the spleen as well as in the secondary lymphoid organs. These B cells that decide to stay within the spleen as well as they decide to go out of the spleen and they go and reside in the lymph node also. These B cells are referred to as something called follicular B cells. These are the future follicular B cells. Remember, these future follicular B cells are the ones that come out of the spleen and form the mature B cell colony in the blood, and those are the ones that enter the lymphoid organs. I mean, typically the lymph node, that's what I'm trying to talk about. These are secondary lymphoid organ, this is the lymph node, and they form a follicular B lymphocyte. So that's what is going to form the follicular B cell. And remember, in between you have transitional stages. The transitional stages, I mean, the immature becomes T1 B cell the moment it enters the blood. These T1 B cells are selected again in the spleen, where they either become dead because they don't go for selection, they become T3 B cells, or they survive the selection process and they become T2 B cells. T2 B cells, which tend to reside only in the spleen. We call them as specialized B cells called marginal zone B cells. These are different type of B cells. And those B cells that decide to stay in the follicle of the spleen, as well as they tend to go to the other lymphoid organs like lymph nodes, they are called as follicular B cells, which enter these are the future follicular B cells, which enter the blood as mature B cells and go into the lymphoid organs and reside in the follicle of the lymph node as a follicular B lymphocyte. So these are some of the important process that happens in between, which is very easy to understand, but I didn't mention it. So while going through this process, because B cells are going to undergo a lot of selection process while moving through this. So at the pro B cell stage, there are no selection process that is going to happen. But at the pre B cell stage, so there is one important selection process that happens. This is called a positive selection. This is called a positive selection. Pre B cell stage. This is what we refer to as something called a positive B cell. So what you can see in the positive B cell selection is, I mean, usually what happens is, I have not mentioned here in the pre B cell stage, but in the late pre B cell, suppose for example in the late pre B cell stage, that happens, this positive selection, where the B cells, if you see here, the surface immunoglobulin, this is what we refer to as something called a B cell receptor. I have told you, typically in the pre B cell stage, you really don't express the surface immunoglobulin, but in the late pre B cell stage, there are certain chances that the surface immunoglobulin will be usually expressed. So surface immunoglobulin may be usually positive in the late pre B cell stage, that is called a B cell receptor. I told you already, in the B cell, immunoglobulin in the surface is what we call as a B cell receptor. So I told you the idea of the positive selection is to know whether the receptors are functional or not. We saw in the T cell basics itself. So here we need to know whether the B cell receptor is functional or not. How will you know that? So they are exposed to certain antigens. So these are generally non-self antigen. These are some non-self antigen. They are going to expose this to certain non-self antigens. So if the receptors are going to work, suppose if the B cell receptors are functional, which means if they bind with this non-self antigen, which means at least they have to try to bind, isn't it? So which means it's a functional BCR. So this will go selection and they will survive. Suppose if they do not bind, to the antigen that is exposed in the late pre-B cell stage, so we term that this B cell is going to be, this B cell receptor is going to be non-functional. Clearly, there is no doubt about that. This is a non-functional B cell receptor. So which means these B cell clones will be deleted. So which means these are not useful because they are not having any functional BCRs, isn't it? So like I already told you, in the thymus, in the cortex, there is selection process, isn't it? In the deeper cortex, I told you the T cell receptors will be subjected to binding with MHC class 2 or class 1 antigens. If they do not bind, they will be deleted there itself because they don't have a functional TCR. Similarly, here also the same process happens. Here they do not have a functional BCR, means the particular B cell clone will be deleted completely. So this is what happens. And now you have something called immature B cell stage. In the immature B cell stage, this survived B cell will, they only will go through the immature B cell stage. So if they go through the immature B cell stage, they again undergo another selection process called negative selection process. They have to undergo another selection process called a negative selection process. So what do you mean by a negative selection process? negative selection process means, again, the B cells will be exposed to, in this condition, they will be exposed to self-antigens, like same thing like what happens in the thymus. Thymus in the medulla, this process happens, where the T cells will be challenged with self-antigen through IR gene by medullary thymic epithelial cells and medullary dendritic cells in the thymus. So that we saw for T cells. Similarly, here also they will be exposed to the self-antigens. Any B cell that is binding strong binding is usually an autoreactive B cell, but like in thymus they generally go for apoptosis if they bind strongly, but here there is some option given to the B cell which we'll discuss. Suppose if it does not bind strongly, no strong binding. Suppose if it does not bind strongly or very weak binding, or if there is no binding, then B cells will survive. So these are not autoreactive B cells, so these B cells will survive and they pass on to the next stage, that is called a transitional B cell stage, which then progress to mature B cell and follicular B cell stage. If there is a strong binding, the B cell will be given an option. The B cell will be given an option. So where the B cell can undergo either apoptosis or energy. Apoptosis means death, energy means, I told you, the B cell cannot bind with any antigen in the future forever, which means it's an inactivated B cell forever throughout its entire life, and its lifespan also will be shortened. So this is what we call energy. So either they will go for apoptosis or they are going to go for energy. Second option, they can go for something called receptor editing. There is some process called receptor editing where the B cell will be, yes, they will be allowed to edit their receptors, but in thymus there is no process like this. But in the bone marrow for the B cell alone, this is some privilege is given for the B cell, where the B cell will be allowed to or given a chance to edit their receptors so that they will change the receptors and somehow try to survive. So during the receptor editing, again the challenge will be given, the self-antigen challenge. So if they do not bind, for example, now if they do not bind to self-antigen, then now they can survive. So which means second, this option is there, so they can survive. So if the receptor editing is failed, if this is a failed receptor editing, which means they still bind to the self-antigen, again they are going to go for apoptosis or energy. So this multiple rounds of receptor editing can happen. It's not only one round of one chance will be given. So there will be multiple chances the B cell will be given. If a lot of chances are, depends how many chances, it all depends on the genotype of the particular B cell. So in all these chances, if the B cell failed to produce a BCR that does not bind with self-antigen, so they will go for either energy or apoptosis. What determines whether they will go for apoptosis or energy? That usually only micro and core immunology textbooks will give this. Suppose if the B cell is exposed to multivalent self-antigen, if it's a B cell is exposed to multivalent self-antigen, and if it's binding to multivalent self-antigen, they are going to go for apoptosis. And if they bind with a soluble self-antigen or fluid phase antigen or a soluble self-antigen, so that B cell will go for energy. So that's what. So you have to understand this important process, something called receptor editing, that happens during the negative selection process at the immature B cell stage. So I hope it makes a little bit of sense. So now once the receptor editing is successful, or if the B cell does not bind with any self-antigen strongly, they are going to go for transitional B cell stage. From the transitional B cell stage, they become immature B cell, which becomes a follicular B cell. Either when they come out of the blood, the same future follicular B cell we are going to call as mature B cell, and then they go to the lymphoid follicles and become follicular B cell. Or if they stay in the spleen itself, these particular B cells, if they stay in the spleen itself, they will simply called as follicular B cells because they are not going to enter the blood. So very simple, as simple as that. So that follicular B cell and immature B cell don't make a big fuss. If it stays in the spleen itself, that cells that do not form marginal cells, another chances they become follicular B cells, isn't it? So they reside in the spleen itself, means they straight away they call follicular B cells. If they come into the blood and then go into the lymphoid follicles and settle there, so those B cells while coming into the blood they are called as mature B cells, and once they go into the lymphoid follicles they will be called as mature follicular B cells. That's all. But there is no much fuss in that. You all know that. So in the lymphoid follicle or a splenic follicle, a B cell may be exposed to the antigen. So this B cell is the one that will be exposed to the antigen in the lymphoid follicles. Once they are exposed to the antigen, they will become activated, and this is what we call activated B cell. In the activated B cell stage, there are two options are there. The main option is to become a plasma cell. So this plasma cell is the one that is going to secrete the antibodies. And there is second option is also there. This activated B cell may try to reside in the lymphoid organs itself for future exposure. These are what we call something as memory B cells, which I have not shown. So this is a second fate of activated B cells. So either they can become a plasma cell, antibody secreting plasma cell, or non-antibody secreting memory B cell, where they just stay, which means if memory B cells are something, like they wait for the antigen, once the same antigen comes again, they don't go through a lot of process of activation and all. These are already activated only. Immediately they will differentiate into plasma cells and they start secreting antibody. That's for quick and immediate response, which we'll discuss later on. So these are some of the important aspects of how these B cells are found out. Now let us see the surface markers, CD markers. This CD markers terminology was introduced by WHO in 1984, maybe I think in November 1984. That is the time where this B cell CD markers have been, first time has been, cluster of differentiation markers has been introduced in the nomenclature by the WHO. So let us see what are the CD markers, important markers. I told you, first is the most important, the TDT. TDT, terminal deoxyribosyl transferase. This TDT is an enzyme that is seen only in very primitive B cells. Typically in the stem cells it will be seen in the pro B cell and pre B cell stage it will be seen. It will not be seen in any other B cell stages. Very important point. And you know very well this CD34 is a stem cell marker. Once it commits into a particular lineage, usually the CD34 will be lost. Exception, certain transitional B cells may still start exposing CD34, but really is, to be honest, only for exams at least, remember only the stem cells will expose this CD34. And after that you cannot see this CD34 at all. Wherever you see there is no CD34 which I have drawn. So there is no CD34 except few transitional cells may show, which I will tell in some time. Then you can see in B cell lineage plus primitive cells, you can see these two important cell lineages, that is the CD43 you can see. This is seen only in these two stages, that is the pro B cell and the pre B cell stage. The CD43 will be seen, which means it's not seen in the stem cell, but it will be seen only in primitive B cell, not immature or mature, only primitive B cell stages you can see the CD43 marker. So possible. And next one important marker which I have shown, you can see this is CD19. You can see the CD19. You can see the CD19. The CD19 almost comes everywhere, isn't it? So which means it is coming from your pro B cell stage and persists up to your plasma cell stage, which means the CD19, that is the reason why it is called a pan B cell marker. Even though I can show you a lot of B cells which are CD19 negative also, but to be honest, the CD19, since it's seen across the B cell lineage, but it's not seen in the stem cell, the moment it commits to the B cell lineage, the CD19 will be exposed, and it is seen throughout the B cell stage, including the activated B cell, everything the CD19 is seen. So that is why the CD19 is also referred to as something called a pan B cell marker, which we discussed already in the previous video. This is a pan B cell marker. And you can see other important things. Very importantly, I want to show the surface immunoglobulin where it will be exposed. Remember, like B cell receptor is made of, very importantly, their immunoglobulins. I told you already, if this is the surface of the B cell, the mature B cell will have a B cell receptor which is nothing but a surface immunoglobulin, and there will be two complementary receptors will be there, which I told you. This is called immunoglobulin alpha and immunoglobulin beta, otherwise referred to as CD79A and 79B. These are complementary B cell receptors which are also very important for the entire BCR function. So you can see initially the CD79A means it's nothing but this immunoglobulin alpha, which is a complementary B cell receptor. So which means in the pre-B cell, the pro B cell stage itself, you are actually forming the complementary CD99, that is cytoplasmic CD79A, that is cytoplasmic immunoglobulin alpha, that complementary B cell receptor. That cytoplasmic, it is starting to get exposed in the cytoplasmic area. You can find it out in various immunohistochemical stains. So this is what happening in the pro B cell stage. This cytoplasmic CD79A is what we refer to as something called a pro B cell receptor. Pro B cell receptor, which might be exposed to the cell surface also. This is what we refer to as, this only the complementary receptors will be seen here. The surface immunoglobulin will not be expressed at the pro B cell stage, that's why this is called a pro B cell receptor. And I told you, in an immunoglobulin you have two, isn't it? So these are the heavy chains and you have two light chains also, isn't it? You have two light chains also. So which means sometimes in the pre-B cell stage, not sometimes, in the pre-B cell stage, they will start expressing this surrogate light chains. The cytoplasmic mu will start they will start to express, and they can also, in the late stages, they can also express, a B cell receptor which will be very primitive. This is called a pre-B cell receptor. Previously I called that's a pro-B cell receptor, where they will be expressing in the late stages only the immunoglobulin alpha, CD7, a complementary part. Now they will start expressing a very, very premature form of a B cell receptor, which will contain only the light chains. These are also called as surrogate light chains. This is also referred to as something called SLC, otherwise referred to as something called a surrogate light chain. So this is what we refer to as something called a pre-BCR, surrogate light chain. So this happens, this cytoplasmic CD17NA usually happens in early pro-B cell stage. This cytoplasmic CD17 becomes cell surface CD17NA in the late pro-B cell stage. Similarly, cytoplasmic mu chain will happen in early pre-B cell stage, and this will become surface surrogate light chain or mu chain in late pre-B cell stage. So this is what we refer to as pre-B cell receptor, or otherwise something simply referred to as something called a surrogate light chain. So this is what is going to undergo the selection process. So fine. So this is what happens in the pre-B cell and the pro-B cell stage. Now you can see, now the surface immunoglobulin as well has been expressed, and typically the surface immunoglobulin tends to be something called a IgM. Remember, the moment it becomes an immature B cell stage, immature B cell will express this surface immunoglobulin, mature B cells will express this surface immunoglobulin, follicular B cells will express this surface immunoglobulin, activated B cell also will express surface immunoglobulin, but you can clearly see a plasma cell will not express a surface immunoglobulin. Plasma cell also do not express a surface immunoglobulin. Remember, even in the activated B cell, one important point is there is a stage called centroblast stage, which I will discuss in detail in some time. The centroblast stage do not express a surface immunoglobulin, but there is something called a centrocyte stage which starts expressing surface immunoglobulin. Clear? So in general, you can remember the most important point is the plasma cells do not express surface immunoglobulin. So where is the immunoglobulin in the plasma cell? Instead, they express something called cytoplasmic immunoglobulin. The reason is they are having so much of ribosomes and endoplasmic reticulum work going on. So they are going to secrete actively this antibodies. So they are going to secrete them. There is no point for a plasma cell to sense antigen. They have to secrete these immunoglobulins into the plasma. So that's why they are positive for cytoplasmic immunoglobulin, but they may not be positive for surface immunoglobulin. That's also surface immunoglobulin will be lost in a plasma cell, but remember they have cytoplasmic immunoglobulin very actively going on synthesis. So because they are activated and they are differentiated into to perform their terminal function, that is antibody secretion. So that's what is all about the immunoglobulin. Then you can see there is one more receptor called something called a CD22 receptor. You can see initially CD22 synthesis starts in the pro-B cell stage itself, where the CD22 will be only cytoplasmic, but later on the CD22 starts becoming expressing on the surface, and CD22 is seen in almost all the B cell stages exception for a plasma cell stage. Again, plasma cells do not express this CD22 remaining, except for the plasma cell stage, everything somehow they will express the CD22, but remember in the pre and pro B cell stage the CD22 will be cytoplasmic only from the immature B cell stage, mature B cell stage, then follicular B cell and activated B cells will express the surface CD22. Apart from that, they will have pro and pre will have only cytoplasmic CD22, but they don't have surface CD22. Plasma cells neither have surface or nor have CD22 anywhere in the cytoplasm or in the surface. So this is what happens. And the next marker is about the CD20, where you can see the CD20 is that B cells which have successfully underwent the positive selection, that is after the pre-B cell stage, so they form the CD20. So CD20 you can see it is seen in the immature B cell, it is seen in the mature B cell, it is seen in the follicular B cell, it is also seen in a lot of activated B cell. Again, your plasma cells will not contain CD20. At the same time, please do remember This pre and pro B cells will not have CD20 again. This pro B cells and pre B cells will not have CD20 once again. Clear not? So only the immature, mature, follicular and activated B cells will have CD20. The plasma cells and the primitive B cells will not have CD20 expression on the surface. And finally you can see one more thing I have to say, that is CD27. You can see I have mentioned something called a CD27 here. You can see CD27. So why I put only CD27 here is CD27 is a marker of activated B cells. Only activated B cells, and beyond that they will be seen in memory B cells, they might be seen in your plasma cells. Even memory B cells will express CD27. So which means only activated B cells. They will not be seen before the activation stage. Even follicular B cells will not express CD27, which means CD27 is one of the activation markers. The moment the B cell gets exposed to an antigen, they start expressing this CD27. So CD27 is an activation marker, activated B cell. So this CD27 is also very important. And finally, one final marker which I want to tell is on the CD138. Final marker which I want to tell on the CD138, the CD78 and CD319. So all these things are classic plasma cell markers. All these things are classic plasma cell markers. Remember, all these things are classic plasma cell markers. Very, very important for exams. I am not telling 138 is only a plasma cell marker, because certain times this activated B cells also might express the CD138. But in general, CD138 and this CD78 and all these things are generally considered as a classic plasma cell marker. That too, this 138 is very, very important for exams. This is a classic plasma cell marker. And finally, the CD79A, if you see, again the CD79A is somewhat similar to the CD22. You can see this CD22 is expressed from the late, this pro B cell stage till the CD79A will come. Usually the CD79A will go hand in hand with the CD22 usually. Wherever you see the CD22, you can also see this CD79A, which is nothing but a complementary B cell receptor, that is immunoglobulin alpha and beta. So this is CD79A. Very importantly, remember the characteristic feature of the plasma cell is, I told you plasma cells will lose the surface immunoglobulin, plasma cells will lose CD20, plasma cells will lose CD22 also, but they will retain this CD79A. Very, very important point. Plasma cells, normal plasma cells will definitely retain this CD79A. But suppose if it's a malignant plasma cell, this is a very important applied concept. If it's a malignant plasma cell, that is a plasma cell neoplasm, which is nothing but a multiple myeloma, then this CD79A may be lost. Remember, in a normal plasma cell, CD79A will be retained. Despite all the other markers being lost, CD79A will be retained in the your normal plasma cell. But a malignant plasma cell, like a plasma cell neoplasm, like a multiple myeloma, that malignant plasma cell might lose a CD79A and they might be negative for the CD79A. Very, very important. So these are the important B cell markers. This diagram looks a lot of messy, but I think you can understand, the core concepts of this particular image, what has happened. So finally, now you can put it in a nutshell. Remember, this CD27 is an activation marker, so which is seen only in activated B cells. Remember, CD20 is seen in almost all B cell lineages except your primitive B cells, that is pre and pro B cells, primitive B cell lineage and plasma cell lineage. So these are the most important things which lose the CD20 markers. Remember, CD79A is seen in almost all B cell lineages. CD79A is seen in almost all B cell lineages, but remember, it is cytoplasmic, usually in primitive B cell lineages. Primitive B cell lineages, it is cytoplasmic, whereas in plasma cell lineage, in all others, it is surface, that's all. But apart from that, CD79A is almost in all B cell lineages. CD19 is seen in all B cell lineages on surface itself. CD79A is seen in almost all B cell lineages in the surface itself. That is why the CD79A, I told it will be called as something called a pan B cell marker. And remember, the surface immunoglobulin will be seen in again all B cell lineages, exception of where you don't see the surface immunoglobulin is in the primitive B cell lineages. Primitive B cells will not have the surface immunoglobulin, whereas and plasma cells also will lose the surface immunoglobulin. Remember, in the primitive B cells, I told you in the pro B cell stage, pro B cells will have something called your pro BCR, where they might express only this immunoglobulin alpha, that too in the cytoplasm, that is CD79A, that too in the cytoplasm. Whereas in the pre-B cell stage, they can express something called a pre-BCR, not a full-blown functional B cell receptor, it's called pre-BCR, where they have only surrogate light chains. In the early stage, they will have cytoplasmic mu, but in the late pre-B cell stage, they will have a surface mu itself. That is what we refer to as surrogate light chain or pre-B cell receptor. But remember, in the plasma cell, they will not have any surface immunoglobulin, but they might have a cytoplasmic immunoglobulin. That is very, very important, because cytoplasmic immunoglobulin for secretion of this immunoglobulins. That's what happens. So then remember, the CD138 can be seen in activated B cells, certain activated B cells, but not always. Activated B cells may or may not show, but definitely almost all the plasma cells will show CD138. Very important, like plasma cell marker, the CD138. So these are some of the important markers that you have to know. And CD22 also goes hand in hand. I told you CD22 always goes hand in hand with the CD79A. So you can write as like this, CD79A, so which is almost equivalent to CD22. CD22 is somewhat similar to CD79A, where again CD22 in primitive B cell stages it will be seen in the cytoplasm, whereas in all the other lineage it will be seen in the surface. But remember, CD22 will be, only exception being, it will be absent in plasma cells again. CD22 will be absent in plasma cells. Clear? But all the other B cell lineages will have CD22 either on the surface or on the cytoplasm. So these are some of the core concepts. Like I've given a crunch points about the B cell surface markers. It's very complicated to see in the diagram. If you see plus minus, it gives a lot of tough thing and difficult thing to understand. But I think I've tried to make it as simplified as possible by telling all this important information regarding to the B cells and the selection process and the transitional B cells also. With this particular segment we can finish, but before that let us see the transitional B cell markers also. I told you there are three types of B cell. One is called a T1 B cell, another one is T2 B cells, and third one is called a mature B cell. So what are the markers if you ask me? CD10, CD34, CD23, CD93 and CD45RA. CD45RA, receptor alpha, the CD45RA. So remember, this transitional B cell will express CD10, CD34, they will express the CD93 also. Very important point. All these things are very important, CD34, CD10 and CD93. But remember, the CD93 is what we actually generally refer to as something called transitional B cell marker. Transitional B cell marker. Remember, all these things will not be expressed by CD10, will not be expressed by this mature B cell, which I have not drawn here at all. CD10, please be very careful. CD10 I have put only in bone marrow compartments. I didn't tell you this. You can see the CD10 is seen only in the bone marrow compartments. I am not drawn this CD10 here, which means a mature B cell is not going to contain a CD10. Very important point again. So CD10 and CD34 definitely not mature B cell, and CD93 will also not be expressed by the mature B cell. Very important point. And remember, CD45RA is again like a pan B cell marker, which will be expressed by all types of B cells. There is nothing like only this transition cells will represent. Even mature B cells will have the CD45RA. Remember, only the CD23 can differentiate between a T1 and a T2 cell. That's why this is important. So T1 and T2 cell, how will you differentiate it? The CD23 will be negative in a T1 B cell and CD23 will be positive in a T2 B cell. Whereas CD23 again will be positive in a mature B cell also, but that is not important. Really not important. CD23 expression by mature B cell is not important, but this is the one that differentiates, because T1 B cell will not have CD23, whereas T2 B cell will have CD23. But remember, apart from that, CD10 expression, CD34 expression, CD93 expression is common for transitional cells, but both T1 and T2 cells, but it will not be seen in mature B cells. Very important, very, very important point. At the same time, your CD23 is the one that differentiates between T1 phenotype and T2 phenotype, where it will be negative in T1 phenotype and positive in T2 phenotype. So CD45 array will be seen in all the B cell lineages usually. So these are some of the important markers of the T1 and the T2 B cell. And I didn't tell you about the memory B cell marker. Memory B cell, they will ask you one important marker. I told you memory B cells will still retain that CD27 definitely. There is no doubt about that. But very important memory B cell marker is something called a CD45RO. CD45RO. CD45 is a very, very important memory B cell marker. CD45RO is a very, very important memory B cell marker. So remember, I told you your activated B cells might become either plasma cells or memory B cells. Activated B cell may become plasma cells or memory B cells. Remember, plasma cells don't come straight away from active B cells. First, initially they become a plasma blast, then only they can become plasma cells. But remember, these plasma cells will be CD38 positive. Even your plasma cells and plasma blasts also will be CD38 positive, and any activated B cell again will be usually CD38 positive. But remember, this memory B cells will be CD38 negative. This memory B cells will be CD38 negative. Again, a very important point. Remember, so how you can tell it's a memory B cell is, first you can tell memory B cell will be CD19 positive, which is a pan B cell marker, and there will be CD27 positive, which is an activation marker, which means it's an activated B cell. Then it will be CD38 negative, which means in the activated B cell, it is not a plasmablast or a plasma cell or simply an activated B cell. Finally confirms by CD45RO positive, which means it confirms it's a memory B cell. That's all. This is how you tell it's a memory B cell. 19 positive, it's a B cell lineage, not a T cell lineage, because the CD45RO positivity is also seen in memory T cells also. That is the reason first you have to confirm it's a B cell lineage by saying it's a CD19 positive. Then you can tell activation positivity, that is CD27 positivity. Then even though if it's an activated B cell, it's not a plasmablast or a plasma cell or just an activated B cell. It's beyond that. That's why it's CD38 negative. Finally, you confirm it's a memory cell by telling it's CD45RO positive. See that these are the important markers of a memory B cell, which is again important to understand. Now, I think we made a good deal about understanding the CD markers and understanding all these stages of the B cell compartments, peripheral compartments, central compartments, and all these things. So let us move on to the B cell subtypes. Remember, we have discussed all this, whatever I told you, we have discussed only about the bone marrow. Only about the bone marrow is what we have discussed. We have not discussed something about the fetal erythropoiesis, which happens because there is separate type of B cells that give rise to that originates from a fetal erythropoiesis. I didn't tell you that at all. So let us assume you have something called a fetal liver. Fetal erythropoiesis. In the fetal liver, you tend to produce, in the fetal liver also there is one more process that is happening, that is called an hematopoietic stem cell. This hematopoietic stem cell can give rise to certain B cells. These are actually referred to as something called B1 cells. These are also called as something called a B1 B cell. But these B cells that are coming out from the bone marrow, these are actually referred to as something called B2 B cells. These are actually referred to as B2 B cells. B2 B cells are of two types. Already I told you, it could be your conventional follicular B2 cells or your splenic marginal zone B2 cells. All these are coming from the bone marrow through the bone marrow maturation process. But the fetal liver can give rise to your B cells, a specific clone of B cells in the fetal life itself. These are referred to as something called B1 B cells. Like the idea of what are these B1 B cells is we really don't know, because this B1 B cells, we believe it's a part of innate immunity, number one. Probably innate immunity, we really don't know. Probably it could be a part of innate immunity. But B2 cells are definitely, which are coming from the bone marrow and maturing through the bone marrow, these follicular B cells and marginal zone B cells in the spleen. Typically we call them as your adaptive immunity B cells, that is B2 B cells. But B1 B cells is something different. And location of this B1 B cells is also very, very different. The location, if they ask you where you see this B1 B cells, they are seen typically in the body cavities. The pleural fluid, then peritoneal fluid and all these things, in pericardial fluid, in body cavities you see them. You don't see in the lymph nodes and the secondary lymphoid organs. Very important. They migrate and locate in the body cavities. Probably they form a primitive first line of defense where they prevent the organisms from entering through the body cavities and gaining access into the body and the blood. So maybe, so this is what the idea between the B1 and the B2 B cell is. So we didn't tell you. So now let us discuss the differences between a B1 B cell and a B2 B cell, that is follicular, conventional follicular B cell, and a B2 B cell which is a marginal zone B cell. Marginal zone B cell. So where they are produced? First produced, if they ask you, this is produced in the fetal life itself, that is before birth itself they are produced. But typically these two follicular B cells and marginal zone B cells come only after birth, when the bone marrow takes over. Then only they start producing this typical follicular B cells. Then if they ask you the prevalence in the body, how much B cells they contribute to, less than 5% of the B cells will be B1 B cells. Almost 70 to 80% will be B2 follicular type B cells, and 15 to 20% approximately will be splenic marginal zone B cells. That's also B2 B cells. And what about the variable region? There is something called variable region in the B cell receptor. B cell receptor, this is the variable region and this is the constant region, in the immunoglobulin. So this is the variable region. So what will be the feature of this variable region? It will be very restricted. It will not be that much, which means the clones are not that much. It's very restricted pool. Very small number of antigens it can find out and identify. But it's very diverse, but it's partly restricted, not very diverse, not completely restricted like B1 also, it's partly restricted. Then you have renewal. Remember, actually, quite interestingly, these are self-renewing cells. Self-renewing cells, which means they can renew themselves. They have that stem cell potential, this B1 B cells. But no, they are not self-renewing, and the renewal is not possible. And they typically found in the secondary lymphoid organs only. They are replaced from the bone marrow only. They cannot renew themselves. They have to be replaced. Once they are dead, they have to replace by new cells from the bone marrow stem cells only. They cannot be replaced. But remember, they are not renewable, but in generally they will be long-lived. But here they will be short-lived only, and they will be constantly replaced from the bone marrow. But these are usually long-lived. These marginal zone B cells are generally long-lived B cells, even though they do not have any self-renewal capacity. Similarly, what is the primary location? I told you already, the B1 B cells, the primary location is the body cavities. Body cavities, whereas B2 follicular cells in the follicles of the lymph node, follicles typically of the follicles of the lymph node and the spleen may be seen in the GIT, respiratory mucosa, tonsils everywhere. And B2, they will be restricted to the marginal zone of the spleen. Primary location is the marginal zone of the spleen only. You won't see anywhere else this particular type of B cells, primary location. Then after this you can see the immunoglobulin production, spontaneous, without getting exposed to antigen. Spontaneous immunoglobulin production is very high. Actually it's quite low with this. What is the immunoglobulin secreted? Secreted immunoglobulin, typically it is of IgM more than IgG, whereas it is IgG more than IgM. Once again, the marginal zone B cells secrete more of IgM more than IgG. Then finally, you have antibody avidity. The secrete antibody, what is the affinity towards the particular antigen? Actually, it is low affinity. You have high affinity, the B2 B cells from the follicles. Here you have intermediate avidity. So the plasma cells that are generated from these particular B cells, these B cells are the ones once get activated, they are going to differentiate into plasma cells and memory cells. So plasma B cells, plasma cells that are produced are generally short-lived here. These are long-lived plasma cells usually, but they can also produce both short-lived and long-lived plasma cells. The same thing applies to marginal zone B cells also. They can also produce both short-lived as well as long-lived plasma cells. And whether they respond to carbohydrate antigens or not, yes. And they don't usually, and they do respond to carbohydrate antigens. Whether they respond to any protein antigens, very poor, yes, they respond to protein antigens. Remember, I told you these are form of innate immunity, that is why they're responding more to carbohydrate antigen. These are adaptive immunity, that is why they are responding more to protein based antigens. That is the reason, as simple as that, B2 B cells. Then whether they are T cell dependency or not, actually they are not, they are T independent activation, which I will go to discuss in some time, whether what is T dependent and T independent activation. Here they are T dependent typically. Here they can be activated either by T dependent as well as T independent, which means both principles are happening here. They're somewhat intermediate. So both T dependent and T independent activation are there. Whether they can produce memory B cells, I told you plasma B cells, but memory B cells or not, no. They cannot produce memory B cells. They can produce memory B cells, but here we don't know whether they really produce memory B cells or not. We have no idea. But definitely follicular B cells is a known thing. It's a very extensively studied thing. They do produce memory B cells, but there is no evidence that your B1 B cells will produce any memory B cells. And I told you type of immunity that they are generated is typically innate immunity, whereas here it is acquired or adaptive immunity. Here they give both types of immunity, innate as well as adaptive immunity. And whether they go for any somatic hypermutation, which we'll discuss in some time, whether they go for somatic hypermutation or not, answer is no, answer is yes, answer is yes. They go for somatic hypermutation, but the maximum rate of somatic hypermutation is again for follicular type of B cells only. Then maybe markers, if you ask me. Markers very important. This B1 B cell important marker is the CD5 positivity, very important, very important marker, CD5 positivity, whereas this is what the exam point is, CD5 negative. B2 group means it will be CD5 negative, irrespective of whether it's marginal zone or a follicular B cell. And typically they will be CD43 positive, whereas they will be CD43 negative. Both will be CD43 negative. Similarly, CD23 negative is these two, CD23 negative, CD43 and CD5 will be markers of this B1 group of B cell. CD23 will be negative in both marginal zone B cell and this B1 B cell, but CD23 will be positive for follicular B2 cell. Definitely, it's a very important marker, CD23 positive. Then CD19 will be positive in all these three things, telling it's a B cell lineage. I told you that's why it's a pan B cell marker that must be positive in all the three lineages. I mean any B cell, that is not something very important. There will be IgM positive and IgD positive, but IgM will be very high, but IgD will be very low. But this is the same thing that happens here also. IgM will be high, whereas IgD will be very low. But these are, we are talking about the surface immunoglobulins. Similarly, here IgM will be very low, but IgD levels will be very high on the surface. So this is the major difference, one of the differences between a follicular B cell and other two subsets. But in general, B1 B cells will have CD5, CD43 positivity, whereas B2 group will not have this CD5 and CD43 positivity. Clear on? So these are the idea, but all these three things will be CD19 positive because it's a pan B cell marker. They should have that CD19 positive, then you can tell it's a B cell lineage in the first place. So you can understand or not. So these are the different types of B cell subsets you have in the body as a whole. But apart from the other groups of B cells you have, these are the basic B cell subsets you have. Then you have B cell activation process. So we are entering into a zone called a B cell activation. There is a whole lot of image which I'm going to show on how a B cell is going to get activated. Whole lot of image on how the B cell is going to get activated. But what I can tell is, before going into the B cell activation, it's also important to understand there are two basic types of B cell activation. That is called a T dependent activation and one other thing called a T independent activation. So what do you mean by a T dependent activation and T independent activation? In general, T dependent activation is more effective and more efficient, where the B cell gets help from the T cell and then gets activated and then differentiated into plasma cell or memory cell, and the plasma cell secretes antibodies. This is very efficient. But T independent activation is also there, where it is also important. I'll tell you why. Because this T dependent activation, because first T cell should be activated, then B cell should be activated. You should go through all this process of somatic hypermutation and clonal selection and all. Then only it starts secreting antibodies. It takes some time. So who will come for the first defense? The moment the antigen is encountered, I mean in the adaptive immunity areas like secondary lymphoid organs, immediately you need some response, isn't it? It's not like you have to wait for all these responses to develop and then only you will develop immunity against the antigen. It's not like that. So initially itself you should develop some immunity, a short term, a quick first line, should not call first line defense, adaptive immunity only, but initially you should have a quick response. So that quick response is generated by this T independent process. It's, even though it's not that efficient, that quick response serves as some immediate response to the antigen that is already present in the body. So this is the basics of what you mean by T dependent activation and T independent activation. So let us see what are the differences. First, let me tell you the T dependent activation here. Then I can tell the T independent activation. T dependent activation we also called as something called a secondary response, and T independent activation we also called as a primary response. I told you the reason already. This T independent activation is something for a quick response. Immediately antigen is there, so their body gets panicked and they produce a T independent response. But there are some cells which get activated and they go through a process, organized thing, so they go for T dependent activation also, which is more organized and more effective also. They come slowly, but it is also important. But in the initial period you need this T independent activation. Clear? Now this is what we call the primary response and the secondary response. So then what are the antigens? So if you ask me the properties of the antigen, the properties of antigens in T dependent activation are very complex, whereas in T independent activation it's very simple. Antigens only can promote this T dependent, but complex antigens cannot promote this T independent activation. Then what is the structure? Structure will be more of a protein. That's why I tell more of a protein based antigens. I told you this protein only is very important for adaptive immunity. So protein based antigens like glycoproteins, actual peptides, amino acid sequences, then lipoproteins, then protein nucleoprotein complexes, which means everything should be protein based. Protein, nucleoprotein complexes, all these things. But here if you see, most of them will be non-protein things like carbohydrates, like polysaccharides. Polysaccharide means very important for pneumococcus, do remember. So pneumococcal polysaccharides, so polysaccharides. Then dextran polyvinyl pyrrolidone. This is also very important component of many bacteria. Then LPS, gram-negative bacteria, lipopolysaccharide, all these things. These are more of a non-protein antigens. That's what I'm trying to tell. Then what are the antibodies that are induced? Antibodies that can be produced is IgG, IgM they can produce, IgA they can produce. These are three principal antibodies. Plus or minus they can also produce Ig response also, they can produce IgD response also, which means it's a very, very polyclonal response. They can only produce IgM antibody, they cannot produce IgG or Ig. Class switching is not possible, that's what I'm trying to tell. IgM antibody only they produce, which means they are polyspecific, they are not polyclonal, but polyspecific, only germline antibodies. They're just polyspecific germline antibodies that only they can produce. Then T cell activation is there or not? Yes, definitely. Who's going to activate these cells? These are called as specialized T cells called follicular T helper cells. These are a form of CD4 T helper cells only. These are follicular T helper cells which are present in the lymph nodes. These are something we call as follicular T helper cells. That's what is going to activate these B cells, forming the helper function. And here there is no T cell activation. T cell activation is not there. And location. Location, typically it works in the germinal center of the spleen, where it works for B1 cells and B2 marginal zone cells. This kind of T independent activation typically works for B2 marginal zone, splenic marginal zone B cells and B1 B cells which are present in the body cavities. But typically lymph node follicles and the splenic follicles, this follicular germinal center B cells undergo this T dependent activation process only, typically. Then whether memory is there or not, immunological memory, yes, no. I told you, because it's a sudden quick response, it's not meant for the future memory or class switching or anything. So I told you this class switching is there or not? Answer is yes, no. I told you already. No memory, no class switching. What's a quick response is T independent response. Then booster response will be there or not? Booster response is not there because it's only quick response again, not meant for additional boosting effect and all. No memory, so no boosting effect. So no booster response. So development of antibodies, this will have at birth itself, but this will take 3 to 18 months after birth. So these are some of the like differences between T dependent activation and T independent activation. But the major differences are this particular, whether activation, the location, memory, class switching formation, all these things are very important questions for exams from immunological perspective. But in general, I feel like this is more of a very primitive topic, but it's better to understand. Only the story which I told you is important. T independent is mostly of a quick response, a primer response, but T dependent is more of an organized response. It will take some time. Till that you need some initial, fight back. That is what is given by the T independent response. Apart from that, there is no memory, no class switching. It's just a quick rogue response that is generated by the immune system. That's all. So let us now focus on the T dependent response. T dependent response. Let us see what happens in the T dependent response. So this is what is very important. T dependent response. This happens in the lymph node follicles and the splenic follicles. So this is going to happen in the follicles of the lymph node and the spleen. This is the areas. These follicles are the areas in the cortex where you get adaptive immunity, where you get this secretion of these antibodies and T cell help, and all these things are happening in these areas only predominantly. So to understand this, it's very difficult to understand just by a theory based explanation. So I have put an image so which will help you to really understand about what is happening over here. So how you can make it understand this, because you can see the first I've shown you a lymph node and took a part of the lymph node and saw this is the area of the cortex where this yellow color zone is something called a primary follicle. Remember, only if the B cell gets activated in the primary follicle, they become a secondary follicle and generate a germinal center and a mantle zone and all these things which you saw in the basics of adaptive immunity part in the lymph node section. But now, let us see. First, it's a primary follicle where the antigen has not been exposed, so the B cells are not yet activated there. So they only form a primary follicle there. So the primary follicle is what is the typical B cell zone. You can see that's what I have written. So this primary follicle in the green areas, these are the proper cortex, these are the B cell zones. I told you these are the proper cortical areas. These are the cortex only. All these are cortex. All these are cortical zones. These are B cell areas, but there is another area in the cortex itself. This is called a paracortex. These paracortex are the ones which is going to contain these T cells, which you have seen already. So that's why in this diagram it's been mentioned. This is the paracortex. This paracortex is where you call it as a T cell zone, and the cortex, the proper cortex area, that is what we are going to call it as a B cell zone. So now I have given a lot of steps 1, 2, 3, 4, 5, 6, up to so many steps we have given in this particular image. But let us break it down and keep it really, really simple. Let us assume the B cell is getting exposed to an antigen. Remember, antigen is coming in through the blood or through the lymph into the lymph node. That's the first step. Antigen is coming. Remember, once the antigen is coming into the, your lymph node is filtered in the lymph node by the lymph, or it's coming through the bloodstream. First thing that happens is the macrophages get activated and the dendritic cells are going to get activated. Clear? The dendritic cells are going to activate. So because these are the two antigen presenting cells, the macrophages and the dendritic cells are the two most important antigen presenting cells. We told you already. Remember, the dendritic cells are located in the paracortex, whereas these macrophages will be, dendritic cells will not be present, will be migrating to the paracortex to help the T cell, whereas typically the macrophages will move into the B cell zone to help the B cells. Clear? Very important. The macrophages will migrate to the B cell zone to help the B cells, whereas the dendritic cells will migrate to the paracortex to help the T cells. So now you can see the T cells now are getting activated by the dendritic cells. The T cells in the step number 2, you can see the T cells are getting activated by the dendritic cells, whereas in step number 1 the B cells are trying to get activated by the macrophages. Clear? But remember, this form of activation of B cells may be important or may not be important, but let me tell you. So the B cells are initially getting activated by the antigens by macrophages, and the T cells in the paracortex are getting activated by your other form of antigen presenting cell called dendritic cell. Now what happens is the B cell tries to move into the paracortex, the T cells tries to come out of the paracortex, which means now the B cell is also activated by the macrophage because the antigen is getting exposed. the B cell that is selective for that particular antigen. I'm not telling you all the B cells will be activated. The B cell that has recognized that antigen, which has a B cell receptor that has recognized that particular antigen, is getting activated, and it's trying to move into the paracortex, but it will not go into the paracortex. Similarly, T cell that is getting activated by the dendritic cell in the paracortex is trying to come out of the paracortex, but they won't come out of the paracortex. But remember, usually at the junction, I can draw here, usually at the junction, what happens is the T cell which is activated by the same antigen and the B cell which is going to activate the same antigen are going to interact. So which means the T cell, for example, if two friends are getting beaten by the same fellow, they shake hand, isn't it? And they make a plan to, destroy the fellow who's beating up these two fellows. So it's like that. So the B cell which is activated by the same antigen by the macrophage, and the T cell which is activated by the same antigen by the dendritic cell are telling hello to each other, and they're making a plan to destroy the antigen which is the villain here, common guy for them. So they shake hand at the junction of the cortex and the paracortex, but some books do tell that the B cell go into the paracortex because T cells are like bosses, they don't come out of the paracortex. But ideally it happens in the paracortex and cortex junction, that's where it happens. So they shake hands with each other because both have recognized the same antigen. They tell, okay, hello B cell, the T cell is telling, and hello T cell, the B cell is telling, and okay, you have the antigen, okay, I have also seen the same antigen, and the interaction happens to the B cell receptor and the T cell receptor and the MHC complex, because B cell which has recognized this antigen is going to express the antigen through the MHC class 2. MHC class 2. If you take the basics of adaptive immunity and see in MHC, I would have told, activated B cells also can express this MHC class 2 and, antigens, which you can go and look back now if you want. So they can also express this MHC class 2 protein. So they are going to interact with CD4 of the activated T helper cell here, follicular T helpers here, and your MHC class 2 of the B cell, both are going to shake hands with each other. So now this interaction is something, that is going to make one more thing here. So there is something called CD40-46, CD40-40L interaction, which I want to tell. So it is not the only interaction that is happening. So I told you this is the MHC class 2 and CD4 interaction that is happening. Apart from that, one more interaction happens that is not mentioned here. What is the interaction here? There is something called CD40 and 40 ligand. Remember this interaction, I'll tell you what is that. This is CD40 that is expressed on the B cell side and CD40 ligand that is expressed on the T cell side. And this interaction of the CD40 and 40 ligand is absolutely essential to ensure that this particular B cell will get activated and that particular B cell will survive. If the CD40-40 ligand interaction is not present, means that B cell will not get activated. Very important, because remember the CD40 ligand is a marker of something called the T cell has recognized an antigen. That is what the CD40 ligand I will think about. So if there is no CD40 ligand and the B cell is reacting with your T cell, means it's very likely to be an autoreactive B cell and it's not going to function at all. That is the reason why this like a co-stimulatory signal, apart from the BCR and apart from the MHC class 2 and TCR signal, this CD40-40 ligand interaction is absolutely important to make the B cell go into the next stage. If it's not there, they are not going to go into the next stage. The moment this CD40-40 ligand interaction happens, this T cell is going to secrete interleukin 4, which means then only the T cell has to know that we are interacting with the right B cell. So sometimes a T cell might be expressing an MHC class 2, T cell might be interacting with some antigen, sometimes it could be an autoantigen also. So both these are very important to understand that both are reacting with the right antigen. So the expression of the right antigen is once the CD40-40 ligand interaction is complete, the T cell also tells yes, okay, that's the right antigen. So we both are friends now. So this will give a signal in the form of interleukin 4, and this interleukin 4 is a very, very important survival signal for this particular B cell. Then only this B cell will progress to the next stage. Otherwise this B cell will not survive and they are going to go for energy and apoptosis. It's not going to survive anymore. So let us assume it has interacted with the right antigen. Now it is moving to the next step, and both here you can see the B cells the B cells that are survived this CD40-40 ligand, which means it's a right interaction, and the T cell also, which knows it's a right interaction, both come out of the respective zones and this area, and they enter the primary follicle once again. And they enter the primary follicle. Once they enter the primary follicle, so now you can blow up this primary follicle in bigger scenario, and you can see what happens in the primary follicle. In the primary follicle, they create a reaction. So this particular area, so which I can put in shaded area. So this area, within this area, this is what we refer to as something called a germinal center reaction. So both the activated T cells as well as the activated B cells will enter the will enter the primary follicle, and they create a reaction within the primary follicle called as germinal center reaction. For example, I told you the B cell in the cortex, to better understand, a T cell will shake hand with each other. B cell, I told you, will interact with the T cell. Both the B cell and T cell interact at the cortex and paracortex here. And once the interaction shaking hands is complete, both are going to run away into the primary follicle. In the primary follicle, if you zoom it and see, they go into the primary follicle and they create something called a germinal center reaction. Germinal center reaction, which typically contains these activated B cells. This germinal center is the one that contains these activated B cells, whereas the remaining B cells that are already present in the follicle, primary follicle, that is not taking part in the antigen based reactions, are pushed to the side, and that is what we refer to as something called a mantle zone. Remember, and once the germinal center reaction is formed, obviously automatically the mantle zone also will be formed. So once the germinal center and the mantle zone is formed, this follicle is no longer called a primary follicle, so it gets transformed into a new name called a secondary follicle. And it gets transformed to a new name called secondary follicle, which means both the B cells and T cells which have got activated now enter the primary follicle, and they create a germinal center reaction where the cells that take part in the antigen elimination program, they only form the germinal center reaction, where the other B cells that are not taking part in this particular reaction, they go to the surrounding mantle zone. That is what we refer to as something called a, the entire thing, the mantle zone along with the germinal center reaction. Now the primary follicle will no longer called as primary follicle. Once the germinal center and mantle zone is formed, they will be now called as a secondary follicle. So that is what has happened here. So now in the germinal center itself, don't get confused, the mantle zone is generally dark. The mantle zone is generally dark and the germinal center is generally light, which you have seen already in the the basics of adaptive immunity. In the secondary lymphoid organs, I've told you, the germinal center is generally light in nature. But in the germinal center itself, you have to, even though they are overall called as light, but if you put under immunofluorescence and see, in the germinal center itself, there are two areas. One is called the dark zone and the second one is the light zone. Don't get confused by these names. Germinal center in histopathology, if you see, the germinal center reaction usually will be light and the mantle zone will be dark usually. The germinal center, which is usually light, will have a central dark zone and the surrounding light zone. Remember, the entire germinal center is generally light only in histopathology, but in IHC, if you see, in immunofluorescence, if you see, in the germinal center itself, there is a surrounding, overall it's a light zone, but there is a central dark zone also will be there within the germinal center. But don't get confused by this thing, not very important, just to make you understand I'm telling you all these things. So what happens in this particular area is, now if you see where the B cells are getting activated, so that's what is going to happen. So I told you already, the B cells which are coming in from the cortex, so these are activated B cells that are coming from the cortex, that are entering from the cortex. These are activated B cells. Remember, the activated B cells has received signal from T cell. This has received survival signal from T cell in the cortex paracortex interaction. Survival signal from T cell in the form of CD40 ligand interaction, which has resulted in IL-4 secretion from the T cell. So the B cell, now it's activated, that is entering the germinal center area, that is the germinal center reaction. And these B cells, they enter the dark zone. In the sense, they are the ones that form the dark zone. and they turn into certain group of cells called centroblasts in the dark zone. They turn into certain group of cells called centroblasts, which I can put separately like this. So these are called as centroblasts in the dark zone. So what centroblasts are trying to do is something quite superb. So what they really try to do, this centroblasts, is because they feel that whatever the B cell receptor affinity is there. Now you know this is the B cell receptor, it's an immunoglobulin, surface immunoglobulin. So the B cell receptor affinity for a particular antigen can be increased, which means they wanted to be more powerful and more selective for a particular B cell, particular antigen. So they wanted to change this B cell receptor to even more, maybe I can write like this, even more super selective B cell receptor, and that is what they want to transform. They want to transform into very selective and very powerful specialized killers. So that's why they go through a process. They want to become more specialized. That's why how they do that process is very elegant. They undergo a principle called something called somatic hypermutation. That's what happened in this entire centroblast. They go to a process called something called somatic hypermutation, and I can write as SHM. So what will be happening here is something called a somatic hypermutation. Remember, again, for the B cells to get activated and to go into centroblast and for the somatic hypermutation, the CD40/40 ligand is really important. That's why I told you the single most important interaction that is important for the entire germinal center reaction and antibody production is the CD40/40L interaction. Now even the drugs are being designed against the CD40/40 ligand interaction for autoimmune disorders and all, but anyway, fine. So this is the most important interaction over here. That is the one that triggers the somatic hypermutation. What really happens in somatic hypermutation is there will be activation of this enzyme. I told you they want to become more powerful. So in the cytoplasm of the B cell, there will be one enzyme that will be activated, that is called AAD enzyme will be activated. That is called activation induced cytidine deaminase. Cytidine deaminase, that's called activation induced cytidine deaminase. This is called AAD. This AAD is the one, what AAD does is it produces random cuts and random assortments of the B cell receptor genes, that VDJ recombination, that's what we call. I didn't tell much about those VDJ recombinations, but that's what happens here. So they keep, putting random thing, which means if they produce random, cells like this, it's very difficult. Listen, they will be producing a lot of types. For example, let us assume a B cell receptor is like this. Now there is a possibility. Let us assume there are two B cell receptors. We'll draw like this. So this is a B cell, this is another B cell with B cell receptor. So now by activation induced cytidine deaminase, this B cell undergoes for somatic hypermutation, and there is a lot of possibility. Let us assume the antigen is something like this. Antigen is something like this. So let us assume this B cell receptor becomes something like this, which means it becomes more specific for this particular antigen. So now it can become more specific and more affinity. The B cell receptor becomes more affinity for this particular antigen. So this is a success. This is good. But let us assume the second type of mutation, another B cell goes for somatic hypermutation, but this B cell produces an B cell receptor which is something like this, which means this antigen is not going to even fit into this B cell receptor, which means this is a a negative mutation. This is a positive effect. This is a positive effect, but this is a disastrous. This is negative. This is a disadvantageous mutation. This is not an advantageous mutation. This in fact is a disadvantageous mutation, and there is no point in keeping these B cells, and these B cells has to be deleted, and only these B cells has to survive. How the centroblasts are going to, how the body will know that this B cells have to survive and this disadvantageous mutations should not survive. Very simple. How do you do? For example, you have 1 lakh students or 1,50,000 students or 50,000 students, whatever numbers you have, and you have to select only 4,000 or 5,000 appropriate candidates. What do you do really? Keep an exam, keep a test, and keep a neat exam. That's what happens here. We are going to do an exam. That's it. So these centroblasts that are coming out of this somatic hypermutation, remember, they will be subjected to the exam by follicular dendritic cells. For example, if there are 100 B cells that are undergoing this somatic hypermutation process, there will be only very few follicular dendritic cells outside the dark zone that will be presenting these antigens once again. So now automatically you are creating all the a lot of B cells may have receptors that have affinity for that, increased affinity for that particular antigen. But obviously the receptors that don't have affinity will fail this process. They cannot bind with the antigen expressed by the follicular dendritic cells outside, and that will go for problems. But if suppose a lot of B cells have underwent an advantageous mutation. For example, a lot of B cells have produced an advantageous B cell receptor that has a good affinity for that particular antigen. But we don't want all the B cells. Like exams, we want only the top candidates. We only want the correct candidates. So reduce the number of seats. So which means you are going to select a very narrow cluster of candidates who are topmost. So that's what we want. So that's what happens in this particular B cell. So what is going to happen is the centroblasts that come, even though they have improved affinity for that particular antigen, obviously B cells centroblasts that don't have improved affinity, they are going to die. They cannot bind with the antigen at all. They don't receive any survival signal. But the B cells that are having improved affinity, they come out of the dark zone, and when they search for the follicular dendritic cells, there will be very few follicular dendritic cells will be available, and only very, very selective B cells, selective centroblasts that are having very high affinity for the antigen only will bind with the follicular dendritic cell, because the number of follicular dendritic cells are very, very less, and the remaining centroblasts, even though they have higher affinity, they fail the test because compared to the affinity of those which are having high affinity, this moderate affinity also will go, and only the highest affinity centroblasts will bind with the follicular dendritic cells, and only they will survive. So that's what I'm telling you, only they are going to survive. Only they are going to survive. And for example, if they do not bind, means they are going to go for apoptosis. That is the idea. So this B cells I have written here, these B cells which do not bind here, they go for apoptosis, and this centroblasts that bind with this follicular dendritic cells will survive, and they are the ones which are now called as centrocytes. Now they are the ones which will be called as centrocytes. The centrocytes leave the dark zone and enter the light zone, in the same germinal center itself. In the light zone, now once again they will be exposed to re-challenge. They will be exposed to this T cell help is needed. Once again, it's not only about the survival. These centrocytes now has to once again bind with the T cell. That is very important, the T cell receptor. To make sure that it's really the right antigen now, because if you are, the next step, the B cell is going to produce antibodies. So this is the second crucial step where again the T cell confirms that it's the right antigen that the B cell is now selected against. So how many exams the B cell have? So now the centrocytes also once again subject to the exam really to know that it's the right antigen, and now they bind with the T cell receptor MHC class 2, and once again your CD40 ligand interaction is so crucial, and if this is not there, once again the B cell centrocyte, even though it came out of a lot of selection process, it doesn't matter, it will not survive. As simple as that. And they're going to go for death by either apoptosis, or they will go for energy. So this is very, very crucial, and once this interaction is complete, the CD40 ligand interaction is complete, the T cell will secrete some cytokine. The T cell is going to, this follicular T helper cell is going to secrete some cytokine, and this cytokine determines the next step. This centrocyte that has received this particular cytokine and the survival signal, that is CD40 ligand from the T cell, will either differentiate into either a plasma cell or a memory cell. It all depends on what cytokine the T cell is giving rise to. So that is what is going to happen. So suppose if the T cell receives the B cell receives a particular cytokine, it will become a plasma cell. If the B cell receives a particular cytokine from the T cell, it's going to differentiate into a memory B cell. So this is what the entire process that is happening. So in order, if you want to summarize all this process that is happening, so first you have a B cell. So it's a very simple thing, just we'll take 2 minutes for this. You have a B cell. This is a mature follicular B cell. This is a mature follicular B cell. This is a very mature and a follicular B cell. And you have a T cell, and both will be activated. Initially they will go for macrophage activation. This will go for dendritic cell activation. both are going to interact with each other. Macrophage and dendritic cell both are going to interact with each other. So now once they are getting activated, during this interaction I told you it's actually the MHC class 2 and the T cell receptor interaction. At the same time you need this CD40 ligand interaction and also secretion of IL4 from the T cell that makes the B cell activated. So now the B cell will be activated. So now the activated B cell and the T cell both are going to enter and form a germinal center reaction. Germinal center reaction. In the germinal center, the activated B cell will form centroblasts. Activated B cell will have centroblasts. Centroblasts will go for something called somatic hypermutation. The moment they go for somatic hypermutation, if it's a disadvantageous mutation, they go for apoptosis because they cannot bind with follicular dendritic cell. If it's an advantageous mutation, they bind with the follicular dendritic cell and they survive. If it's an advantageous mutation, they survive. Once again, they need T cell help, and the survived B cells now we will be calling as centrocytes, which enter the light zone. Now this survived centrocytes is going to again get this follicular T helper cell. This is the follicular T helper cell, CD4 T helper cell. This is the follicular T helper cell help. Again you have this MHC class 2 and T cell receptor interaction. Again you need this vital CD40 ligand interaction. This only will make the centrocytes differentiate further. If this is the case, they differentiate further, which can differentiate either into a antibody secreting plasma cell, or you can develop something called a memory B cell. Always do remember, the plasma cells that are generated by this particular principle through all this activation process, that is T dependent activation, will generally be long lived plasma cells. It's not be shocked, it's going to secrete antibodies for a long time. That's why you have this IgG antibodies that are present in the body for a very, very long time. So then finally this plasma cells, remember one more important thing is these plasma cells will not reside in the lymph node or the spleen. Usually these long-lived plasma cells will enter the bone marrow. Remember, only short-lived plasma cells will remain within the lymph node, and especially the medullary cords and medullary sinuses, that's where the short-lived plasma cells will remain. But the long-lived plasma cells generated by this process will generally go into the blood and migrate into the bone marrow. From there they will be secreting the antibodies. That's why remember, your multiple myeloma is a problem in the bone marrow. That's why they produce lytic lesion in the bone marrow. It's not a disease of the lymph node. In multiple myeloma, it's a plasma cell neoplasm. It's a disorder of the bone marrow. The problem is in the bone marrow. The long-lived plasma cells always migrate to the bone marrow, from where they secrete the antibodies. It's a very, very important concept. Again, migration to the bone marrow. Clear? So remember, during this interaction, this CD40 ligand interaction, the cytokine, remember the cytokine that is secreted by the T cell will determine what type of particular so it determines, the cytokine is the one that is determines two things. Determines whether it will become a plasma cell or whether it will become because plasma cell is going to secrete antibodies, whether it's going to become plasma cell or whether it's going to become a memory B cell. So that's what is going to determine. So once if your plasma cell is formed, again the antibody should not be the same IgM antibody. So the antibody also should be different. So again, there is something called class switching of these antibodies. There is something called isotype class switching of these antibodies. This class switching of these antibodies is also determined by the cytokine that is secreted by the the particular T cell. For example, what I am trying to tell is, suppose if the cytokine that is stimulating coming from the T cell, suppose the T cell secretes a cytokine called interleukin 4. Cytokine called interleukin 4. They are going to produce IgG or IgG1 antibodies. Typically IgE is the most important. They are going to produce Ig or IgG1 antibodies. If the interleukin coming from the T helper cell is follolled T helper cell interleukin 5, now they will produce IgA antibodies. This is called again class switching. If they receive something called TGF beta, then they will produce something called immunoglobulin A, or they might produce immunoglobulin 2A, depending on where the lymph node is. If it's a mesenteric node or if it's your gut-related node, they will predominantly produce IgA, or if it's going to be your lymph node, then they will produce this IgG2A. And suppose if the cytokine released by the T cell is interferon gamma, then they are going to produce IgG antibodies, especially your immunoglobulin G3 and immunoglobulin 2A. Please note that the moment the class switching happens, this class switching is generally irreversible, which means the moment the class switching happens, it is permanent, and the plasma cell that is producing this antibody will produce only that particular antibody. They are not going to change the antibody production once again, which means it's an irreversible process, class switching. And again, remember the follicular T helper cell, what cytokines they produce, depending on that only determines whether it will be a plasma cell or a memory cell. At the same time, it is the one that is going to determine whether your class switching and what type of antibody your plasma cell is going to produce. So this is what is very important. So in order to form memory B cells also, you need a very important cytokine help as well. So typically the cytokine that is needed for producing this memory B cell is interleukin 10. So this is a very important cytokine that is important for producing this memory B cell. So this is what we refer to as something called interleukin 10. So this is also a very important process that is happening over here. So these are the entire process that you have to know about the B cell maturation and development. So how it happens, so what is called somatic hypermutation, what do you mean by centroblast, what do you mean by centrocyte, then how they do this class switching, how they do this memory B cell development, all these things all depends on. It's a very beautiful and elegant process how the selection process happens, and this is what we call, these are one of the things that you have to understand about the B cell basics. So with this we can finish off this. Then there are still some more B cell basics which are left, we'll be discussing in the part 2 of the same video.